Hi there, geometry students. We are starting Unit 2 today, and we are talking about essentially an introduction to proofs. There's quite a few things that we're going to be covering, including kind of an introduction to some logic. So if you've been taking philosophy, this can be a little bit of a review of maybe some of the things that you've talked about. But this is definitely a new chapter. So if you were counting on some more easy review before we got into the real difficult material this year, well, not so. Most of this, what you're going to see is new stuff, unless you've consciously gone out and sought it. So here in lesson 1, we're going to be talking about inductive reasoning. So ICANN 1 is use inductive reasoning to discover patterns and then make conjectures. And then 2, show a conjecture is false by finding a counterexample. Those are the 2 ICANNs that you're going to have to deal with today. So number 1, just a little bit of vocabulary to start off with. A conjecture. What is a conjecture? Well, if you were in a science class, you might call it a hypothesis. They're essentially synonyms, although not quite. It's just, you can say it's an educated guess based on previous understanding. So you're going to you're going to take either some images or some patterns. Ultimately, you take a look at a pattern and use that to make a conjecture, a hypothesis, a guess based on what you've observed. And this is actually what is called inductive reasoning. Inductive reasoning is making a conjecture based on a pattern or previous understanding. An example of this in my real life, I suppose, is a number of years ago I had to go to jury, and when I was the defending, I guess the prosecuting attorney, the one who was trying to show that this person was guilty, this person that was on trial, I guess first of all, was being tried for drunk driving. And the police officer who had arrested him didn't have any actual hard data like a breathalyzer or something like this, but all he was going on was things like, he could see that he looked drunk and he smelled like he was drunk, but he didn't have that hardcore data. And so the prosecuting attorney was trying to make this analogy. If you went into a movie theater and it was dry, and then you came out of the movie theater and the ground was wet, what would you assume had happened? Well, she was counting on everybody saying, well, it rained. Is it possible that something else happened? Well, sure, somebody could have washed their car. I don't know, there are a lot of things that could have happened. But she was trying to make the point that just because, she was trying to make the point that usually if you're using inductive reasoning, you're correct because it follows a pattern. But of course, the defending attorney came up with lots of counterexamples to that. And so a counterexample, at least in logic, if you can find one and only one, or one or more, counterexamples, this proves a statement is false. And so, of course, this lawyer was able to come up with all sorts of counterexamples, and that really kind of shot a hole in this prosecuting attorney's case. All right, so here in example 1, it says describe the pattern and then write the next 3 numbers in the pattern. So looking here, I guess with these first 2, you'd say I would subtract 500. 1,000 minus 500 is 500. But if I continue with that pattern of subtracting by 500, then I certainly do not get the next number in the pattern. And so that can't be it, so I try something else. Well, how about dividing by 2? Does that continue to work? Yes. Is it possible that something else might be the pattern? Well, maybe, but I'm going to make a conjecture based on my understanding of this pattern and, write the next 3 numbers. So we'd say, all right, 125 and so on. And we'll just continue to divide by 2. Here we have what is, well, let's see. 1, I could multiply by 1 to get 1 again, but that's not going to continue for any of the others. 0, well, that's not going to work either. So we have to look for something else, and from time to time you'll get a pattern that is not quite so obvious as operations, and if you're clever, you'll recognize, well, 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. So if I continue with this pattern, 5 plus 8 would be 13, 8 plus 13 would be 21, 13 plus 21 would be, 34. And so if you're familiar with this pattern at all, you'll recognize it as the Fibonacci sequence. And there are a ton of applications of this pattern that show up in art and all sorts of things. Fascinating, and actually towards the end of the year we'll be doing a little work with that. Here we've got not a number pattern, but a pattern shapes in it, and so we see, given the pattern below, make a conjecture about the number of segments in the step with 5 triangles. Okay, well, the tools that we can use to help find patterns is to make a table. So here we're going to have the figure number 1, 2, 3. We want to get out to the 5th one, and then down here we'll just put the thing that we're trying to count. In this case, the segment. So 1. Figure 1 has 3, and then figure 2 has 3, 4, 5, and then figure 3, 1, 2, 3, 4, 5, 6, 7. And so, again, based on what I've seen so far, it looks like it goes up by 2, and we can just assume that it continues to go up by 2, and we have 11 segments in the 5th step. All right, let's see, moving on to ICANN statement number 2, finding counterexamples to disprove a conjecture. So here we have a statement. The statement can either be true or false. A statement is just a statement. And so this one says, if x is an integer, then x squared is greater than 0. Well, that's true upon first glance. If I take 5 squared is 25, that's bigger than 0. And then you think, well, what about negative numbers? -3. -3 squared, well, that's positive 9. That's also greater than 0. So positive and negative numbers aren't coming up with anything. You might think decimals or fractions, but that would kind of yield you the same result. What about if x equals 0? Well, if x equals 0, I have 0 squared. 0 squared is 0. 0 is not greater than 0, it's equal to 0. And so this is a false statement. So my counterexample is x equals 0. These are always nice little fun kind of puzzles that you don't have to think too hard about, but you have to actually get it. So I kind of enjoy inductive reasoning, taking a look, finding a pattern. Obviously I can't give you a pattern, and that would take away all the fun. So enjoy looking through these patterns, trying to figure out what they are.